Yeah, thanks everybody for coming, everybody in person and also anybody on Zoom. Throughout my talk, if you have any questions, feel free to interrupt me. I don't think we have to wait till the end. If you're on Zoom and you have questions, I may not be tech savvy enough to check the chat while I'm talking, but definitely in person. Feel free to interrupt. I don't want anybody to get lost or confused. This hopefully should be a friendly talk, and I hope you all learned something. Okay, with that, I'm Michael, and today I'll be talking about scaling replicated state machines with a technique we invented called compartmentalization. I'll begin by explaining what is state machine replication. And in a nutshell, state machine replication is the problem of we have multiple deterministic state machines, and we want to make sure they all stay in sync. That is a very fancy way of saying we have multiple copies or replicas of some stateful service. For example, a key value store, or maybe a database. It doesn't really matter what it is. And we want to make sure that all of these copies always stay in sync. We want to make sure they don't diverge. If we view a state machine replication protocol as a black box, it accomplishes this doing something like this. We have clients and they propose state machine commands to be executed. If our state machine is a key value store, for example, then these commands would be things like gets and sets. If our state machine is like a database, these would be like queries and updates, things like that. The clients will propose the commands to the state machine replication protocol, and the protocol is going to totally order all of these commands into some log. Here we've ordered the commands y, then x, then z. Finally, the state machine replica is going to execute these commands in log order. So every replica is going to execute, in this example, y, then x, then z. Because every replica starts in the same state and executes the exact same commands in the exact same order, every replica is always in sync. One of the oldest and most popular state machine replication protocols is called multi-paxos, and it looks something like this. A multi-paxos deployment consists of our clients. We also have a number of machines we call proposers, and we elect one of these proposers to be leader. That's the proposer that I draw with a crown. We also have a number of machines we call acceptors, and finally our state machine replicas. You'll notice that the replicas, along with the leader, they're all going to have copies of this log of commands. Multi-paxos executes like this. When a client wants to propose a command, for example, X, it's going to send it to the leader. The leader is then going to sequence the command into the log. So the first command it receives is going to go in the first log entry, the second command in the second log entry, the third and the third, and so on. Here, X is the first command, so it gets put in the first log entry. Then the leader is going to do a round trip of communication with the majority of the acceptors. And for this talk, I'm not going to have enough time to go into all of the finer details of multi-paxos. So I'm not going to have time to explain what exactly these messages are, why they're happening. You sort of just have to trust me on that. But for this talk, it's good enough to just understand the sort of flow of communication and the flow of messages. So here we have a round trip of communication to the acceptors, and you'll just have to trust all the details behind that. And I want to emphasize that here it's a majority. So 2 out of the 3, that's important. Finally, the leader will send the command along with its index over to the replicas. So here it says, hey, replicas, command X was chosen in the first log entry. The replicas will put the commands in their logs and execute them. And then one of the replicas will return the result of executing the command, here X, back to the client. Okay, so just to make sure that's clear, the high level, here's another command. We go client to leader, leader round trip to acceptors, then to the replicas, back to the client. That's the flow. If you understand that, you're good. If you pick up any paper on state machine replication, more often than not, the paper will say that multi-paxos is too slow. Multi-paxos gets bullied by a lot of these papers out there. And by this, I mean that the throughput is very low. And ideally, we could just say, okay, the throughput's low, let's just scale the protocol. But it's widely believed that multi-paxos doesn't scale. That's not true. That's the sort of punchline of the talk. It's not true. I'm going to show you how we can scale multi-paxos. But before I do that, it helps to understand why people think multi-paxos doesn't scale. All right, so multi-paxos has 3 main components that I mentioned. We have the proposers, we have the acceptors, and we have the replicas. Let's look at every component in turn and try to scale it up and see what goes wrong. So first we have the proposers. Here I've drawn multi-paxos with 5 proposers instead of 2 like I had on the previous slides. And if we look at the protocol and how it executes, we go client to leader, leader round trip to acceptors, to the replicas and back. We notice it's the same, nothing changed. And that's because the non-leader proposers normally don't do anything. The only job of a non-leader proposer is to take over the leader's responsibility if the leader dies. But most of the case, the leader is not dead, everything's fine. So adding more proposers doesn't do anything. The throughput will be unaffected. Next up, the acceptors. Here I've drawn 5, I think? Yes, 5 acceptors instead of 3. And if we look at the protocol execution now, we see that the leader has to contact 3 out of the 5 instead of 2 out of the 3. Remember, we always have to talk to a majority. So our protocol is doing everything we were doing before and then some. Every single message we sent before, I'm still sending it, but now I also have to contact more things, which means that our throughput is definitely not going to go up. It might not be affected, maybe, but most likely, actually, this is going to make the protocol slower. Throughput's going to go down because we're just doing more stuff. And finally, if we look at the replicas, it's pretty much the same story. Here I'm drawing 4 replicas instead of 2. We're doing everything we were doing before, but now the leader has to talk to more replicas. So my throughput will be the same, or most likely it'll go down. So in summary, if we increase the number of proposers, increase the number of acceptors, or increase the number of replicas, our throughput will either not increase or go down. Okay, so that's why people think multi-paxos doesn't scale. It does though, we just have to be a little more clever about how we scale things up. So before we can scale stuff up, we first have to identify what is the throughput bottleneck. And for multi-paxos, that is the leader. So why is the leader the throughput bottleneck? There's 2 main reasons. Hopefully they're both relatively obvious. The first is that everything goes to the leader. Every single command is sent to the leader, and the leader orchestrates communication with everything. So every single command goes to the leader. And 2, the leader for every command is doing disproportionately more work per command than every other node in the whole system. And we can see that by counting the number of messages that each of these nodes has to touch per command. I've drawn that here in orange with the little boxes. So for example, the top replica, it has to receive 1 message, so I write the 1. The bottom replica, it receives 1 message and sends 1, so I write 2. The acceptor is similarly 0 or 2, but finally the leader has to do 7. All right, so it's touching everything and it's doing more. That's why it's the bottleneck. We can eliminate this bottleneck by making the following observation, and that's that the leader has 2 main responsibilities. The first is called sequencing, and that's the thing where it takes commands and it puts them in the log. First command and the first log entry and so on. The second responsibility is communication, and that is the entire rest of the protocol. The leader has to communicate with the acceptors, it has to broadcast to the replicas, all that other stuff. Historically, these 2 responsibilities have both fallen on the leader, but that's not strictly necessary. So the big idea here is first, we're going to decouple these 2 responsibilities, and we're going to do that by introducing a set of nodes called proxy leaders. So the protocol now is going to execute like this. We go client to leader as before. The leader will sequence the command as before, but now the leader is not going to do any communication with either the acceptors or the replicas. Instead, it's just going to send to one of the randomly chosen proxy leaders, and then the proxy leader is going to finish the protocol and run all the communication. So responsibility 1, sequencing, that's on the leader. And responsibility 2, we've pushed to the proxy leaders. So why does this eliminate the leader as a bottleneck? Well, if we do the whole message counting thing again, we see replicas acceptors are not changed, but the leader now went from 7 messages down to 2. Now it just receives a thing and sends a thing. So this will either eliminate the leader as a bottleneck or at least alleviate it as a bottleneck. But you might say, well, hold on though, if we look at the proxy leader still has to do 7. And that was that big number that we didn't like. So are we really eliminating the leader as a bottleneck, or are we just shoving the bottleneck over to the proxy leaders? And the answer is that we're eliminating it, and that's because the second of our main ideas, scaling, says that the leader is load balancing these requests across the proxy leaders. So what we can do is just add more. If the proxy leaders are ever a throughput bottleneck, I'll just add more of them because the load is being balanced across them. They're embarrassingly parallel. Okay, so these 2 ideas, decouple and scale, together, those are not new ideas, but we gave them this fancy name, compartmentalization. I just showed you how to compartmentalize the leader, but compartmentalization is a generally applicable technique. You can apply it to more than just that. So let's now look at how to compartmentalize the acceptors. So I said earlier that naively increasing the number of acceptors is going to hurt throughput, not help it. That's true. But we can increase the number of acceptors in a smarter way. What we're going to do is, instead of having just more acceptors, we're going to have more acceptor groups. So here I have 3 groups of acceptors, 1, 2, and 3. And what we're going to do is round robin partition the log between these different groups of acceptors. So the first log entry is going to get chosen by the first acceptor group, the second by the second, the third by the third, the fourth by the first, and so on. And the thing we're kind of taking advantage of here is the fact that for a given log entry, we need a fixed set of acceptors. That's essential. But for different log entries, we don't. We can have completely different sets of acceptors, and that's totally fine. So we're decoupling the acceptors used across log entries. And now the protocol is going to run like this. It looks pretty similar. We go client to the leader sequences, sends to a proxy leader. But now the proxy leader is going to look at the command, and it's going to say, okay, what log entry is this command in? And based on that, it's going to decide which acceptor group to talk to. So here it says, okay, X is in the first log entry. I'll talk to the first acceptor group. If we get a command Y that's in the second log entry, it's going to talk to the second acceptor group. Third command, third acceptor group. Fourth command would go back to the first acceptor group. And much like with the proxy leaders, these acceptor groups can scale. So if my acceptors are ever a throughput bottleneck, I'll just add more groups until eventually they won't be. Okay, that's all I have time to talk about in detail. But if you're interested in this kind of stuff, if you think it's exciting, I definitely recommend you check out the paper. We talk about how to also compartmentalize replicas. We talk about batching and how to compartmentalize batching. We talk about this read optimization. That's probably the most interesting and probably most impactful part of the paper. We talk about how to implement multi-paxos with really high throughput if your workload is read heavy, which I think is not that uncommon. And compartmentalization, we also apply it to a number of other protocols besides just multi-paxos. Okay, with that, I'm happy to take questions.
Yes. So thanks for the talk.
Yeah.
Are there questions from the room? There is a question.
Thank you for the presentation.
Yeah.
Very interesting. I'm just wondering if you ended up introducing any new error modes just because you're introducing new communications in that protocol, and or if the protocol itself is so well designed that's already robust against the introduction of those new agents.
Yeah, no, that's a great question. So the question is like, you introduced a bunch of new stuff. So are there more things you have to think about in terms of making sure things are safe, even when things fail? Yeah, thankfully, multi-paxos is like super tolerant to failures. And a lot of these things sort of get encapsulated in that. For example, a common question is, well, what if a proxy leader fails? But the nice thing is that in normal multi-paxos, if the leader goes and sends messages, those might already get dropped. Those might already fail. So sending to a proxy leader and the proxy leader failing and not sending those messages, that's the same thing as the leader sending it and it failing. So pretty much all of the failure stuff is already captured in multi-paxos. There are maybe some new liveness things you have to think about, but in terms of safety, it's mostly covered.
Okay, it appears there is a question from online.
Yes, so Michael, if you can stop sharing, and
Yeah.
Yian, please pose your question.
Yeah, so I have a question. I can see the point that you decouple the component according to the different tasks they do, and each task can scale independently.
Mhm.
And now my question is it, can I regard it as a method to reallocate resources for different tasks? Is there any other considerations that the tasks must be physically separated, or I can just more smart reallocate resources for different tasks?
Yeah, great question. So when I draw the pictures, I always draw them as separate entities. But yeah, you can definitely start co-locating stuff together physically. Like two of the little circles I drew could be on the same machine. That's something that actually some folks at Berkeley are researching now. Is you don't want to co-locate too much. Kind of this is saying try not to do that decouple, but you do want to co-locate a little bit because sometimes maybe one of these machines is underloaded and you can start co-locating stuff. So I don't have a clean answer to it. I think it ends up being a complicated problem, but there is definitely a balance to be struck there.
Okay, thank you.
Okay, a question from the room.
Did you actually benchmark and measure if you triple the amount of resources, do you get double the throughput or what?
Yeah, great question. So how much do we scale, I guess? Yeah, those details are in the paper. I think we get from multi-paxos on a write-only workload 6.3 times the throughput with 6 times the resources. So that's not bad. And then for the read-only stuff, that depends on it depends on a lot of factors, but then you can start going many orders of magnitude with like same number of resources, 6x. So you can get pretty good, especially on the read-only stuff. But check the paper for the full details.
Are there more questions from online maybe? There is one.
So Rolando, would you like to pose a question?
No, thank you.
Okay.
Rolando is gearing up for his talk, which is next. But I have actually a question.
Yeah.
So So you're scaling Paxos in various ways, also in the amount of by partitioning or compartmentalizing the acceptors.
Yep.
But what could happen, maybe it's not in your use cases, is that there are very many acceptors involved, and you may actually have cross-partition transactions if you do partitioning on the acceptors.
Yeah.
And then still the algorithm could get into non-scalable situations, I would say. Is that correct?
Yeah, so great question. So I think there's two things with the acceptors and with partitioning and stuff. So a common alternate approach to increasing the throughput of something like this would be just partition everything. So have like 20 instances of multi-Paxos for each of 20 partitions. So we are partitioning internally like the acceptors, but the state machine itself is not partitioned. So if you have cross-partition transactions, yeah, there is some sort of partitioning through the acceptors, but your state machine itself doesn't have to be partitioned. So we actually have a nice advantage there. Another thing is that the acceptor stuff I talk about in this talk actually is a simplified version of the real version, which is slightly more complicated and involves like read-write quorum systems. And there's
involves read-write
quorum systems.
Okay.
Yeah, so it's actually slightly more complicated in the paper. We simplify here in the talk just to make it more approachable. It ends up not looking like this super partition thing. It's sort of more like this amorphous blob of acceptors that you sort of slice into. So it's a little more complicated.
Okay, thanks. We have time because there are 3 talks in an hour. So are we done with the questions online? Are we done with the questions in the room? Well, let's thank the speaker. And it's time for the second talk. If I'm not mistaken, it's very early in the morning in Berkeley. Rolando Garcia is going to talk about hindsight logging.
Thank you very much. And everyone can hear me okay?
And we see the slides.
Okay. All right, so I will get started. Thanks everyone so much for joining us. Here I'm going to be switching gears a little bit. I'll be talking about machine learning, model training specifically. And I'll talk about hindsight logging, which is kind of this makeshift data management practice that people in the field of machine learning kind of come up with as a workaround. And what I'll be discussing are some of the systems techniques that we can import from our field in databases to try and help them be more efficient. And it was great following Michael's talk. I think one of the things I learned about compartmentalization is to decouple and scale. And those are both things that we'll be doing. So maybe we can compartmentalize model training replay. So for people who have done model training in the past, trying to remind you of systems such as TensorBoard or weights and biases and MLflow. So these are tools that are specialized for tracing time series data, and they contain visualization and visual analytics dashboards. It's a hot space. Recently, a company like Weights and Biases raised as much as $45 million for its machine learning tools in its latest seed round. And the reason why logging is such an important problem in machine learning is because a lot of the data logging data enables the model developer to assess training as it trains. And these are very long training jobs. So some of this logging data can be training metrics, tensor histograms, and images and overlays, more recently because of explainability and fairness. So I will next cover an example of what logging might look like, and then give you an intuition for what we mean by us saying hindsight logging. So the model developer here will start with a Python script together with an interactive Jupyter notebook in the cloud, something cloud hosted with a GPU. They will run training and then have access to the loss curves or accuracy. They might see that the loss isn't making sense to them. Like there might be a plateau or the training may get stuck at some value. And the model developer may then ask, is there some problem with the gradients exploding or vanishing? Is there a dead ReLU problem? And so on. So then they might ask, well, what were the tensor histograms, at epoch 30? And then this is a problem if you forgot to log the tensor histograms. So how might you recover that data? The simplest way is just to go back to your code, add more logging statements, hindsight logging, and then retrain the model. Then you are able to view the tensor histograms to confirm or disprove your hypothesis. So increasingly, model training is a very long running job. So something as simple as ResNet on CIFAR 100 for 200 epochs can take 7 hours on a GPU. For maybe a postdoc in astronomy, this is not a big issue if they let training run overnight, but it really limits the number of queries that you can ask in a 24-hour period. So what if I told you that you could take these 7 hours and lower them down to 2 minutes to recover the same data? Like, would you be interested in this technique? So next, I'll give you a high-level overview of our solution for this problem and explain how we're able to lower this replay time from 7 hours down to 2 minutes. And so the goal is fast replay, not 7 hours, but 2 minutes. The way that we're going to achieve that is by doing the least work necessary. Skipping irrelevant code or program slicing is one example. And then not duplicating work through memorization is another. So think about functions. If you've already run a function in the past on the same input and you save the value, you can just read the value instead of doing some computation. The other idea is to do that least work in parallel. And model training is a workload that doesn't parallelize easily, but it does on replay because of checkpoints. But we have to be careful about the kind of checkpoints that we take. Otherwise, we might slow down training too much in the first pass. So we will want to balance replay latency and checkpointing overhead with physiological logging. This is a term that Jim Gray coined several years ago. By physical logging, we mean write program state to disk, and logical logging, just write operations or code to restore program state post hoc. And we also want to move logging overhead off the critical path. In Python, we achieve this via fork or one-shot, one-way IPC. So this is the high-level overview of the talk. It's almost like a poster. And then I'll be zooming in into different concepts to try to give you more details or technical details. We also want to make sure that we're doing the fast replay as well as the selective checkpointing, or the record and the replay, completely automatically, because our target audience, again, someone who is a domain expert like the postdoc in astronomy, should be able to get these efficient record replay benefits without a programming burden, without the opportunity of making mistakes. So the intuition for parallel replay of model training. This is the highest level or most abstract example I can give of model training. We have an outer loop that repeats the same training for many epochs. And then at each epoch, we cover the entire training data batch by batch. And we do a stochastic gradient descent step for one example. And then we would do a checkpointing at the end of the epoch. So checkpointing once per epoch. This would produce a trace of writes, or like a schedule. So there's this sequence of SGG steps with intermingled checkpoints. So how might the checkpoints decouple the epochs, and how can we scale them to multiple GPUs? So on replay, any worker is able to read its checkpoint and start working from an arbitrary epoch and only perform its share of work. So checkpoints are chosen specifically to provide embarrassing parallelism, and we can auto-parallelize model training replay, even if there are strong dependencies between epochs, which is the case in model training. So this is going to be the core focus. In this slide, I'm demonstrating the benefit of linear speedup for fixed costs. So what happens is I add GPUs to the problem. So I start out with 1 GPU, and then I add a 4 GPU machine. And then I remember an advisor might say, well, if I have more GPUs, why don't I use those for training? And the thing about the embarrassing parallelism is that there's no communication or coordination involved. So the GPUs don't even have to be on the same machine. I can start adding GPUs for multiple machines, and I continue to get the same speedups. Again, it all stays at the same cost, which, to quote Benoit from Snowflake, in the cloud, fast is free, which is what we're seeing in this plot. So next, I will focus on how we move logging overhead off the critical path in Python. So the way that we want to achieve background logging and checkpointing in Python, logging, again, to remind you, just means serializing and writing of which serialization is the most expensive part. An always level trick to avoid serializing on the main thread is to use fork. So when we fork, we create a child process that is dedicated to serialization and writing, and the main thread is able to resume training without stopping. In this plot, I am showing you the same work being performed, but one does synchronous logging and the other one does asynchronous logging. You can, when the logging volume is heavy, this can actually result in significant speedups. And finally, in order to provide these benefits without a programming burden, we're going to perform static analysis and program transformation. In Python, static analysis is non-trivial. Python is a dynamic language and this is challenging. So we actually use a heuristic technique for side effect estimation, and then we do a confirmation or a check of the logs post hoc. So the instrumentation serves not only record purposes, but also auto parallelism. So we're able to auto parallelize replay for hindsight logging. In this plot, ideal looks like each group of bars having the same height. And we're very close to ideal. So if that were the case, if all of the bars were the same, then that would mean that we're not adding overhead during recording. So the model training run runs just as quickly with or without checkpoint. The auto record, which is the bar on the far right, is the performance that we're able to achieve automatically, and it's able to match or beat a hand-tuned periodic checkpointing of about once per epoch. So then I will cover the updated example of hindsight logging to try to remind you what this might look like. So there's again the training pass, the first pass with checkpointing, and because the checkpointing is very low overhead, it still comes out to about 7 hours, maybe like 7 hours and a few minutes, like 2 or 3 minutes, very low overhead. The query comes up again, like what were the tensor histograms? And this would be something that you missed on the first pass, something that you forgot to log. So you return to your code, add more logging statements, post hoc or with hindsight, and then you replay training, potentially with more GPUs in the cloud. And this can bring it down to something like 2 minutes instead of 7 hours. This system or this paper, we evaluated it on Floor, which is open source software, and it's available on GitHub. So Floor contains this kind of hands-free mode that transforms user code, but it also is a suite of libraries that includes background logging, adaptive periodic checkpointing. So, changing the frequency of checkpointing depending on materialization overheads, automatic memoization, and then automatic parallelization at replay time. So with that, I'd like to thank you for your time and for your attention, and I'm happy to take questions.
Thanks for this interesting talk. Gabor, are there online questions? There's a question from the room.
Hi, this is Mohammed from the Technical University Darmstadt. Can you hear me okay?
I can
Great.
hear you, yes.
So my question is, how does the checkpoint look like? So do you just materialize the state of the tensors, for example, after a couple of steps? And how big is the checkpoint then? And yeah, how do you persist it? Do you persist it or do you just keep it in memory?
Yeah.
Thank you.
So what the checkpoints will include things like the tensors of the model. So we will be checkpointing, for example, the model, the optimizer, and the objects that we select for checkpointing are selected via static analysis. So the static analysis will make an over approximation of the objects that get modified in the loop, and it'll select those for checkpointing. And the idea here is important for us to avoid just taking a blind complete checkpoint, since that would add too much overhead. And the state does get materialized to disk. So the tensor histograms or the layers of the network are going to make their way down into disk, but this is going to happen asynchronously. And it's going to happen in the background by a child process by calling fork.
Are there other questions? Another question from the room.
I have a question about the checkpointing, the overhead. You said that it only adds 2 or 3 minutes on top of the 7 hours. So that's in terms of latency. But how about resource consumption? You're doing the checkpointing in parallel using fork. How much more resources does that use?
Yeah. So one of the things that we noticed about Python, especially when we're running in the cloud, is that there's a large number of CPUs that are available during training. And these CPUs may be used by data loaders to augment the data processing pipeline. But one of the observations that we made was that these CPUs were spending a lot of idle time during training because most of the work was happening on GPUs. So the resource consumption does not increase significantly because we're just making better utilization of resources. And we're not going to fork on every write. We actually have a batching technique where we copy state to protect it from being overwritten. And then once the batch or the buffer fills, then we fork and write to disk. So the resource utilization does not increase. Sorry, the resource consumption. So the total cost from training does not increase, beyond the extra minutes that the job runs for.
There's another question. Thank you, by the way, for the answer.
Hi, Marcus here from Snowflake. I have a very similar question. So you have this first one, which takes 7 hours, and the second one, which takes 2 minutes, which is obviously great, but how does that look like in terms of money? Like if my first run uses 1 CPU for 7 hours and the second one uses 1,000 GPUs for 2 minutes, then it might still be not a big win, right? Like, do you have numbers there?
You're not going to save on money. And there might be some inefficiencies, but the inefficiencies are minimal. So just as a reminder, the replay is embarrassingly parallel. So there's not like too much work duplication that is happening that would result in the kind of inefficiency that would add a lot of cost on replay when you use extra GPUs.
So it's roughly the same cost, but less time. Is that fair to say?
Yes.
Okay. Thank you.
Yes.
Thanks for the question. I have a question for myself, actually. So you're saying, okay, this replay is embarrassingly parallel and it's parallelized heavily in order to make it very fast. But isn't it in practice the case that if you request more GPUs, that you actually have significant latency in getting them? So if you hit that button, you might wait 2 minutes or more, in fact, to get lots of GPUs. Or is that not the case?
Yeah, so I think when I think about this problem, I'm imagining a workload where you're kind of online or providing some kind of service, and then you want to scale without interruption from like 1 GPU to multiple GPUs. And then I can see how that latency would become a problem. In the hindsight logging case is two phases. So there's kind of like the first model training run that happens, and there's checkpointing that maybe gets stored on the S3. And then maybe, on your laptop or on Jupyter, you add more logging statements, and then you can run on a completely different machine afterward. So I don't think you would get billed for the time that it takes to provision. You might have to wait for the resources to become available for you to start running, but it's not like you're providing a continuous service that would get interrupted.
Okay, so you're saying that this is a feature that SageMaker might adopt or something like that.
Yeah, I think the
rather than doing this in your own account.
Right. I think the ideal case right here would be like serverless, like GPU-backed serverless containers, which I know that is an active area of research.
Okay. Well, we have ample time in this session, so I'm just seeing if there are any more questions. There are no more questions, so let's thank the speaker. Thanks, Raoul. Now we are going to go to an in-person talk on, if I'm correct, on in-network transaction triaging. So I will make space.
Okay, I'm going to switch gears again. I think that's the theme of this session. So I'm Theo Jepson from Stanford University, and I'm going to talk about our work, as you mentioned, on transaction triaging. This is a collaborative effort with the University of Fribourg, Università della Svizzera Italiana, and Yale University. So where do transactions spend their time? They spend a lot of time idle, moving through the network and also the host networking stack. And during this time, the transaction is not being processed. And this is because of the separation of concerns between the network and databases. And the network doesn't know what it's transporting. It doesn't know it's transporting transactions, so it can't help the database. But the network has become computational, and we believe it's time for the scope of the database to expand into the network. And why is this especially important now? On multi-core systems with in-memory databases, we can now execute millions of transactions per second. But how can the network deliver millions of transaction requests to the server? The latest network interfaces can barely deliver transactions fast enough. But this requires using more CPU cycles, which are harder to come about. And also the database server has to dedicate more resources to processing the network requests instead of doing what it's supposed to do, executing transactions. And this is because the network adds a lot of overhead. And how much overhead does the network add? We did an experiment to find out. We got the silo in-memory database and we extended it with the network support. And this is what we call NetSilo. NetSilo uses user-space networking to receive UDP transaction requests from clients across the network. And we use this NetSilo to execute transactions of increasing sizes. And we did this by varying the number of rows accessed. And we found that with smaller transactions, the throughput is higher, as you would expect. However, less time is spent executing the transactions. The overhead with small transactions reaches 70%. And with other benchmarks or workloads, we saw a similar thing. TBCC experiences 53% overhead and YCSB 96% overhead. This means that 96% of the time is spent on networking and 4% on executing the transactions. So where does this overhead come from? There are many sources. So first, when a packet arrives, the NIC sends an interrupt to the database server. And this causes context switches, which are expensive. And then the database may be split into multiple partitions, each managed by a different core. And the transactions can arrive at the wrong database partition. And this causes communication between the cores, either moving the transaction or the data being accessed. And then transactions aren't executed in any particular order, but just in the order in which they arrive. And this means that there's poor cache reuse. And another thing which I haven't showed here is that there was also the question of generating the responses. How does the database know which client should receive a response? And this adds some overhead too. And one thing in this setup is that this problem can't be addressed in the server. It's too late there. We have to find a solution earlier in the network. And since the network already does routing, why don't we use it for triaging? So our solution is to start processing transactions early in the network before they reach the database server. And this way, the server doesn't waste CPU cycles on communication. The server can do what it's supposed to do, execute transactions. How do we do that though? With the emergence of programmable networks, it's now possible to do in-network computing. And using this technology, we designed a transaction manager that runs in the network, and it handles transactions before they reach the server. We call this transaction triaging. So transaction triaging coordinates the transaction delivery between the switch and the server NIC. And we've come up with 4 techniques so far. First, we can batch transactions. So we can deliver multiple transactions in the same packet to the database server. And this reduces the overhead per transaction. And then when the server responds, we have to unbatch and send individual responses to each client. We can also steer transactions to the right database core. So this reduces the latency because each transaction goes directly to the core, which is going to be executed. We can reorder transactions. So transactions that have an affinity for each other, for example, transactions of the same type here in the same color, they're executed together. And this improves cache efficiency, cache use. And also if clients don't support advanced protocols like RDMA, we can transparently convert the protocols. So if the client sends a UDP request, the network will translate it into a RDMA request, which doesn't which has lower overhead on the database server. So these techniques may seem trivial to implement on a general purpose processor, but the thing is that we're not targeting a general purpose computer here. We need to build these algorithms for a new breed of network devices. So as mentioned, how hard can it be to implement these algorithms? For example, if we're doing batching, it's just managing a list. How hard can that be? But on this architecture, it's not so straightforward. The problem is that the switches are built to move massive amounts of data and perform computations on the fly. They're not general purpose computers. And in these switches, the computing units are called stages, and they're similar to cores, but they're connected in a strictly forward chain or pipeline. And a switch program specifies the conditions or actions to be performed at each stage. And the program doesn't fetch data, but the data just flows through the pipeline. So it's no wonder that our data structures can't simply be ported to this model. And what we need to do is redesign data structures and processes, the triaging techniques, and they also need to coexist and run together on the switch, which is another challenge. And in our paper, we introduce a class of feed-forward algorithms along with a new pseudocode notation for this model. Let's look at one of the algorithms that we've come up with, the batching algorithm. So as I mentioned, the switch has to maintain these batches, which we can basically represent as a list of transactions. And normally with a list, you have a pointer to the head, to the tail, and maybe a counter. But this doesn't work here because we need an array-based version of the list, and that's not all. Because in the pipeline we can only move in one direction, we have to traverse the entire list for each packet. So let's say we have an update and we need to increment the counter at the end of insertion. If we need to test that the batch is full and then take an action such as drain the batch, it'll be too late at the end of the pipeline because we've already traversed the entire queue. So this is simple to solve. We can just put the counter before the queue, and when a new transaction arrives, we can increment the counter and test it before doing the traversal. So this illustrates just one of the problems that we had to solve, but we implemented different types of algorithms on the switch, and each of these presents different challenges. Like we implemented queue selection, intra-queue reordering, response splitting, and many more protocols or algorithms. And each of these presents different challenges in how we have to use these resources on the switch. And for example, one of them is stages. And the more algorithms we have, the computation spreads on the stages, and we don't have many of them. So there's this constant balance between the data placement and the availability of compute cycles, which makes designing these algorithms an interesting and challenging problem. And did I mention that if an algorithm works in this model, it automatically works at line speed? And that means that we can produce 5 to 6 billion with a B results per second with the latest generation devices. So we're clearly in acceleration territory here. Let's see how well that performs then. So first of all, looking at the batching algorithm, we found that batching increases the throughput for the YCSB-A workload. So compared to net silo, the baseline silo database with user space networking, we see an almost 8x increase in throughput. And compared to the net silo RDMA baseline, we see a double in throughput. So this is with YCSB. What about some more complex workloads? We ran TPCC with an increasing number of cores per warehouse. So here we increase the contention, and as the contention increases, we see consistently with both the baseline RDMA and baseline RDMA plus the batching technique, we see that the throughput decreases, and also we see the BORT rate increase as we increase the contention, as you would expect. The reordering technique, on the other hand, has a higher throughput than these baselines as we increase the contention. And this is because with the reordering, it delivers transactions of the same type together. So they're executed in a way that reduces conflicts. And there are also other benefits of doing this reordering. As I mentioned, there's some cache reuse, and some other performance benefits at the microarchitectural level. In our paper, we have a full breakdown of performance counters showing how when we do not just the caching, but also we're looking at IPC, we see overall increase in efficiency at the CPU microarchitectural level. So you should check out our paper for that. So to wrap things up, with new networking technologies, we're now able to do transaction triaging. It's now a possibility. It's become reality. And as these databases become faster, we need to use triaging to keep up with the speeds of the network. And we've shown that triaging speeds up different types of workloads like YCSB and TPCC. And in some cases, with some workloads, it's even faster to execute them locally than to execute them. It's faster to execute them with request through the network than locally. And this is because we've offloaded some of the scheduling, you could say, the triaging to the network, so the transactions are delivered to the database in a way that fosters faster execution. And so if databases are going to continue to scale, they must consider the entire transaction life cycle. And this must start where transactions start, in the network. So thank you for your attention. And yeah, if you have any questions.
Well, thank you, speaker. Very interesting talk. Are there questions? I see a raised hand from Snowflake.
So I actually have two questions. We look at a very similar problem. I'm working on Foundation DB, and the network is expensive, as you said. So did you explore IO Uring to get rid of the interrupt problem?
Excuse me, can you repeat that? Do we explore what?
IO Uring. That's basically you can kick off a kernel thread. I was just wondering how much that like your solution helps compared with that, because that gets rid of basically all interrupts, at least in a saturated system.
So what our technique is more about, for the steering at least, we use RSS to steer transactions directly to the core that should handle the transaction. So that's more of a question of latency, even under low load, and that doesn't reduce the interrupts though. Then there's also the overhead, the batching technique, and maybe that's more like it amortizes the cost of an interrupt across multiple transactions. So maybe using this IO Uring could reduce the overhead a bit, but there's still overhead within the database server, because it has to, if you're using RDMA, it has to post a read, and and if you're posting a read per transaction, that's expensive compared to posting one read for multiple transactions. So this could be an alternative or something done together
Yeah,
with.
I didn't mean to suggest that it would replace all your work,
Yeah,
just like
but I think
this.
it could be an extra. Yeah.
Yeah.
Yeah, that
Yeah,
if we're using user space, we could. Yeah.
My comment was, I don't think you have access to IOU ring if you're using RDMA. And with RSS, you use the NIC hardware to deliver the interrupt. So it's quite efficient.
You had a second question or maybe some comment?
The second question was more about like, and maybe this is a bit ignorant. I'm not sure that I understood you correctly, but if you group transactions of the same type together, if you use some form of replication in addition to partitioning, don't you start to run into a problem that if your workload produces a hot partition, that you don't distribute the load across CPUs properly, and then you, instead of having one CPU, 3 CPUs doing the work, you have one and your system falls over?
Yeah, I think that depends on the model that we're assuming. We're not using a replicated system. The data is not replicated across the partitions, but we assume each partition handles a different subset. So then that of course is an issue. Hotspots.
Okay, there's a second question from the room.
Thanks for the talk. And my question is, you mentioned that you reward the transactions. And my question is how this rewarding and all the transaction process relates to traditional concurrency control, which cares about correctness of updates, and then it rewards transactions somehow in logical sense. And you are doing something else.
Yeah, that's an excellent question. So this reordering is independent of concurrency control. So when different clients send their transaction requests to the server, there's no serialization. There's no linearization there. The clients don't have, since they're different clients, they don't expect their the transactions could arrive in any order anyway because of network reordering. So there's no guarantee at that level. But within the transaction, we still have the same guarantees for linearizability. Does that answer your question?
Actually, no, because data might be shared between transactions, and then you have to somehow not necessarily serialize, but care about consistency. But let's discuss that offline.
Okay.
Yes, we can discuss things offline again. But there is yet another question from the room. Dominic.
Hi, I'm Dominic Munich. I have a question. It's a follow-up. So does your abort rate increase because you showed that you want to group by similar transactions, so they work on the same data space? So this could be actually increasing the abort rate if you wait and batch them together to minimize the caching or maximize the caching effect. Sorry for that.
Mm-hmm. Yeah, that's a good point. So first of all, I'd like to start by saying that the reordering is configurable. So there are many ways to order the transactions or specify the order in which transactions should be delivered to the database. One such ordering is based on the transaction type, but you could think of other orderings. You could say, I don't want to deliver transactions of the same type together. So you could, which would be the opposite of this. So it really depends on the workload. That maybe delivering transactions of the same type together could, as you said, increase the abort rate. But for this particular workload that we ran with TPCC, we found that this executing transactions of the same type together reduced the abort rate.
Okay, Gabor, are there maybe online questions? No online questions.
There's one.
Philip. Question from the big boss.
Quick question. Hi, thanks for the talk. Any take on how to grow the community of people who are able to program the routers? So what does it take to teach people, I mean, students, how to, do, follow up on your work and build on your work?
So is this a question of how, I mean, is what we did extensible, or if they want to do something from scratch, how?
Both.
to
So what does it
replicate?
take? So, what's the learning curve and how to, get more people involved? It's an important area. We want people to be able to actually follow up on your work.
I think, so as I mentioned, it's not straightforward using this model, because you really have to rethink your programs, your data structures because of this pipeline model. So there's a P4 programming language, which is a domain specific language for this architecture, but it's intended for packet network processing. And I think a step forward could be to come up with other domain specific languages that are more for databases or different types of algorithms running on this. And I think there's been some work on looking at other higher level languages than P4 that can compile down to P4 and then in turn compile down to the switch and this is for different applications like ML or other stream processing applications.
Okay, we still have time and we still have questions.
Hi there. So in the context of more modern databases which are already distributed and have routing processes that are doing some of this work, how would this fit in with that? Would this go between the client and the router? That seems to defeat some of the purpose, but if we went between the router and the servers, then some of the work's already been done.
So in this context, we're looking at a single database server where there's no replication. But I think there's other work which looks at using the switches to help with replication. For example, doing in-network sequencing, so you can sequence transaction requests and do things like state machine replication on the switches to help with coordination and ensuring consistency. But we're looking at just the transaction manager before transactions even reach the database and before they start being processed. So we're assuming in this work we're assuming it's not a partition database. So, but that definitely would be an interesting problem to look at, how to do this triaging with multiple servers in the background while ensuring consistency.
Okay. So I think we have come at the end of this discussion part. Let's thank Theo for this very interesting talk. And we are at the end of the session.